Hello everyone and welcome to lecture 12 of process integration. In this lecture we are going to talk about capital energy trade-off, that is essentially talking about area targeting of the heat exchangers involved in our process. So in this lecture we will talk about different targets for our process. We will look at energy cost, capital cost, and what is the relation of these with the total cost, and how these different costs can be defined based on delta T minimum. We will also talk about area targeting, looking at balanced composite curves, and then we will talk about some other optimization approaches of heat exchanger networks with loops and paths. This lecture relates with the unit ILO 6, that is around examining and evaluating the capital cost implications and how that can be used for area targeting techniques. Okay, so here we are going to look at a new feature of process integration. This feature is the ability to identify the performance targets before the design types is started. What it means that before the designing the hen, we can find out the important parameters, or I can say the important target parameters for the design, which has to be achieved through the design states. Okay, this is a new feature of the process integration in the pinch technology or in pinch analysis. Targeting procedures also helps in the evaluation of alternative hand designs, because many designs or many computing designs which satisfies the constraints of pinch analysis can be developed. Now, which hand design should be accepted? Now, the targeting procedures tells us that we should select a particular design which needs or which meets the targets of the process. Now, if we see the targeting procedure, that can be many targets which can be set before the design for a specified value of delta T minimum. Such targets are energy targets. In the energy targets, we find out the minimum energy consumption through external heating and cooling for a certain delta T minimum value. And when we change this delta T minimum value, this energy target also changes, because the delta T minimum value affect external heating and external cooling. The second target is fewest number of units. Pinch analysis also helps to find out before we design what would be the number of units in heat exchanger. This number of units include process-to-process heat exchangers, heaters, and coolers. So when we find out the number of units, it is a summation of process-to-process heaters, and coolers in the hen. In the third targeting procedure, we find out the fewest number of shells in the heat exchanger network. That means it will tell us that how many number of shells will be present in the total heat exchanger network. Why we have gone for this is because by counting the number of units, we will not get the accurate result about the number of units, as the shells will be giving, because a heat exchanger can be made up of many shells in comparison to one shell, and this happens when we are dealing with low FT parameter. A heat exchanger with single shell and heat exchanger with multiple shells, if you compare the cost, the heat exchanger with a double shell will cost almost double in comparison to single shell. So the number of shells out, or the number of shell targets, will give us a better picture about the heat exchange network. Obviously, if we have designed two heat exchanger networks, Hen1 and Hen2, and Hen2 has got less number of shells than Hen1, one may select the Hen2 because it has less number of shells. Then the fourth target is the minimum total heat transfer area. The heat transfer area of a heat exchanger network gives a fairly accurate estimate of the cost of the heat exchanger network. And hence, before the design, it is always advisable to find out the minimum total heat transfer area as a target. The fifth target is cost targeting, through which we can use the heat transfer area target, and we can use the energy target. So heat transfer area target will provide the fixed cost of component of, and the energy target will give us the operating cost of the process. And we add these two targets to get the annual cost or the cost target of the process. So there are a number of targeting processes that are available in the pinch analysis, and these are very important because we can define these targets before the detailed design to help us direct our design in the right direction. So we talk about different targeting procedures, okay, and the value of these different targets is actually very much depend on the delta T min that we select in our pinch analysis, okay. So if we look at our, for example, temperature enthalpy diagram for our process, so we have hot streams, then we have cold streams, and the value of delta T min dictate how much energy we can recover from this system, and also how much external cold and hot utilities we require to satisfy the energy demands of the process. So if you look at the value of delta T min, and assuming that we are having vertical heat transfer from hot streams to cold streams, so a certain value of delta T min gives us a fixed energy target in terms of cold utility and hot utility. But if you increase the value of delta T min, we see that by increasing the delta T min, our process to process heat transfer decrease, because we have now less opportunity for for the hot streams to reject their heat to the cold streams, and due to that reason, our hot utility requirement above the pinch and cold utility requirement below the pinch temperature increases. Okay, so the value of delta T min dictates the energy targets, as you saw in the first part of the course with Simon. But that is not the whole story, because the value of delta T min also dictate the area of the heat exchanger required for the process. So we know that Q is equal to UA delta T, and if the delta T min value is increasing, and if you keep the Q, let's say, constant, the value of area that is required for heat exchange decreases. Okay, so that's the advantage of increasing the value of delta T min, because although we are not saving on our energy cost, but we are saving significantly on our area cost. Okay, so it means that there is always a trade-off between the capital cost, that is the the cost required to buy the area, okay, because the cost of the heat exchangers that required for process to process heat transfer, or any form of heat transfer, depends on the area of the heat exchanger. Okay, so the capital cost relates directly with the area of the heat exchanger, while the energy cost in its simplest form is related with the hot and cold utilities of the process. Okay, so that is what we call a cost capital energy trade-off. It means that we have to look a balance between the capital cost of the system and the energy cost. And if you look now, the cost of different cost of the system, versus delta T min, we see that for the case of increase in delta T min, our energy cost will increase. And as I said, that because it is going to increase our utility requirements, so that's why the energy cost is increasing. While for the case of capital cost, because delta T min is increasing, our area is decreasing. As such, we have to buy a smaller heat exchanger, so our capital cost is decreasing. Okay, so and if you look at the total of these two in terms of what is the total cost of the system, so we see that the total cost of the system decreases up to a certain value of delta T min, and then it starts to increase after at a higher value of delta T min. Okay. So there is always a balance that we need to achieve when we are selecting different designs. So what normally we do is that we design different Henn networks based on a range of delta T values. And then we look at these different targeting procedures, different targets that we set for our process based on delta T min. And then we select an optimum value of delta T min that gives us lowest value of these targets in terms of the total cost of the system, in terms of the total area, in terms of the total energy cost. And that delta T min is what we call optimum delta T min. And as such, we can actually reduce the cost of our system or the total energy requirement of our system, because obviously at the end of the day, we are running a business. It's an industry, so they want to actually reduce their operating and capital cost. Okay. Now, in this diagram, we are looking at a very simplified case of different costs. So for example, here in energy cost, we are not looking at different forms of energy, because here we are just looking that the energy cost is linearly increasing with delta T min, but we can have situation where the cost of energy can be different because we are looking at different form of energy. Also, in terms of our total cost, we are only looking at energy cost and capital cost, but we are not looking at other maintenance cost or cleaning cost. For example, in heat exchangers, we have, for example, a lot of fouling over time. And it means that all these heat exchangers require significant amount of, for example, cleaning cost and operating cost, maintenance cost. So we have to consider that in the actual design of the system. So here we are just looking at a very simplified process. Now let's look at the energy cost. As I said, that when you look more closely on the energy cost, so the cost of energy is not linearly increasing with delta T min, and the reason being that now we are looking at different form of energy that is required to the process. And by different forms of energy, I mean that, for example, here in this part, we are looking at low pressure steam, while in this part we are looking at high pressure steam. And as we know, that when the pressure and temperature of a hot utility is increasing, the cost of that energy is also increasing. Okay. Also, for example, if we required a more high temperature utility like flue gases or hot oil, we also see that the cost of that energy will be much more steeper compared to, for example, low and high pressure steam. So we have a significant increase in the price over a value of delta T min. Okay. And if we talk about cold utilities, obviously that will be in reverse. So if you have, let's say, high temperature cold utility, the price will be lower compared to if you have a low temperature utility like refrigeration, the cost will be much high. So this non-linearity in the cost of energy with delta T min shows you that different forms of energies are involved in this system. So that is the energy cost. Now let's look closely on the capital cost as well. So in terms of the capital cost, we talked briefly about the area targeting in terms of the, for example, what is or how much area we required for a particular heat exchange to happen in the process. Now the area targeting, and we will talk about area targeting in a minute, is a vital component in determining that how much capital cost we need for the heat exchanger network. Okay, and it also plays a significant role in the capital energy trade-off, as we discussed in the previous slide. Okay, now area targeting can be done by using composite curves, and we see in the next slide. And this area targeting kinds of is directly related with capital cost, because if you have a certain value of delta T min that you decided, you can calculate how much area is required for the process, and then you can dictate it that how much money you need, or what is the cost of that area that you have to purchase in the form of heat exchangers. Okay, this area gives you the area required for the total energy or the or total heat transfer required in the process. Once you have this area, we look at what are the number of units that that are required to actually achieve this area and perform the energy transfer that is required by the process. So when we are talking about number of units, we are looking at, for example, how many heaters, coolers we needed, how many heat exchangers we needed for the process to process heat transfer. So when we are talking about, for example, heat exchanger networks, so there is a strong incentive to reduce the number of matches between hot and cold streams, or in other sense, it is what it means that there is a strong incentive to reduce the number of units, because it is going to reduce the capital cost of the system. So if you have a heat exchanger network 1 that requires 10 number of units, and you have heat exchanger network 2 that requires 15 number of units, so obviously we are going to prefer to use Hen design 1 because it has less number of units. And with the same logic, the idea is that the cost of one big shell and tube heat exchanger, for example, would be less than two shell and tube heat exchangers of the same area as of the large shell and tube heat exchanger. Okay, so we always try to minimize the number of units in our design. And then we look at the number of shells. So why we are looking at the number of shells when we already looked at the number of units? The reason being that, for example, when we are looking at area and energy target algorithm, or when we are looking at the Hen design, these designs are based on the assumption that heat exchange matches are pure countercurrent flow. Okay, so the targeted values will be close to real only if the heat exchanger employed in Hen are only 1-to-1 design. It means that it has one shell and one tube pass. And this type of heat exchangers offer the lowest surface for shell and tube heat exchanger. However, exchangers employed in industry may be 1-2 heat exchanger. It means that it has one shell and two tube passes, or 1-4 heat exchanger, one shell and four tube passes, or even 2-4. It means that it might have two shell and four tube passes. And these designs can involve cross flow, countercurrent flow, or partially mixed flow. Okay. Thus, the effective temperature difference of heat exchanger is reduced compared to pure countercurrent device, because we are using the correction factor Ft that correct for the driving force, and the delta T Lm or Lm delta T gives us the highest value of temperature difference. But when we have more complicated flow configurations, the value of delta T decreases because of the Ft factor. When we are talking about shell and tube heat exchangers, and for example, if we have a long shell and tube heat exchanger where the temperature range of the hot and cold fluid, for example, in the exchanger is much larger compared to the driving force, there may be a situation where a temperature cross can happen. Okay, and these small temperature crosses can be managed in 1-to-2 shell heat exchanger. But if this temperature cross is quite large, we have to split the shell into multiple shells. Okay, and the cost of this each additional shell is going to also affect the capital cost. Thus, the targeting the minimum number of shells are also useful and realistic in comparison with number of unit targets, as it provides a better opportunity to compare different hand designs. That is for number of shells, but now we can have situations in our process, for example, where we are talking about, for example, different fluids or different systems that require additional attention. Okay, so like for example, if giving you an example from my industrial experience, looking at a fertilizer process, for example, a fertilizer production plant, where you use a lot of high pressure streams. So it means that you have to build the shell or build the tubes with more thicker material or stronger material, and because it needs to withstand that pressure, so that is also going to increase the capital cost of the process compared to a heat exchanger that only require normal thickness of the tube, or a low pressure heat exchanger. Similarly, you can have situation where the fluid is corrosive, okay, and it means that you need to use specialized steel that can handle that corrosive fluid, and as such, the cost of that specialized material would be quite expensive compared to when you are handling benign fluids. Okay. Then you have the type of equipment, because these exchangers are not going to be sitting there alone in the process. For every heat exchanger that you are designing based on the number of units, all these heat exchangers are going to require, for example, the foundation for the heat exchanger. It needs to be connected to different piping. It needs to be connected with different valves and all the control equipment. So it means that each number of unit or number of shell is going to actually add a lot of additional equipment cost that is also going to be going to increase the capital cost of the process. And finally, we have the pressure rating, as I explained, that if you're designing a heat exchanger at low pressure that requires a simple steel, the cost will be much lower compared to a high pressure rated, for example, heat exchanger, where you have to use again specialized material or much thicker materials to withstand that pressure, and that is going to significantly increase the cost of your process. So these are some of the factors to look at when we are comparing, for example, capital cost with the energy cost, and a balance of these two costs is what we call capital energy trade-off, because we have to select an optimum value of delta T min that gives us an optimum value or the lowest possible value of the total cost of the operation. Okay, so that is all for this part. Thank you for your time.